Hello, in this presentation I will outline the main results of the tests carried out in the ICTech laboratories from the Universitat Politécnica de Valencia on full-scale timbrel cross faults. Settlement in one of its supports is one of the main causes of damage to this kind of structure, and that's why we decided to include this study within the framework of the SAHC project funded by the Spanish Ministry of Science. During this presentation, we will see a general introduction to cross faults and in particular to timbrel cross faults. We will see also how differential settlements in the supports affect cross faults and how the SAHC project considers this action. Third, we will show the 4 tests carried out, the setup of the test, its construction, monitoring, etc., etc. And finally, I will outline briefly the main results and conclusions drawn from this research. I'm sure that most of you know what a cross fault is. They are the result of the intersection of two orthogonal parallel faults. They are some of the most beautiful structural types the human race has ever built. They have been used for centuries as structural elements in many historical buildings. They first appeared in Europe during the Roman Empire and reached heights of extraordinary splendor during the Gothic period. In a literature review using Scopus, only 48 references were found on masonry cross faults. About 1% of all the reference found on masonry walls, masonry domes, etc., regardless of its importance. That was the reason why we decided to undertake this study within the SAHC project. Timbrel vaults are a particularly efficient type of cross vault. They are also known as Catalan vaults, even though they first appeared in Valencia, particularly in Játiva in 1360. At the south of Catalonia. I'm from Valencia, so I would like to call them Valencian vaults. They are made of 2 or 3 layers of bricks laid lengthwise. The first layer is usually supported by a quick-setting gypsum mortar. Once the first layer is partially complete, it serves as a permanent formwork for the following layers. It has many advantages: lightness, economy, aesthetics. It makes a very, very structurally efficient element. This type of structure are very affected by differential settlement, as we can see in the picture. The picture shows a fallen cross vault in Castel de les Cabres in Castellón. It was built in the 18th century in the north of Valencia. One of the timbrel vaults collapsed due to soil settlement. The collapse and its causes were studied in a master's thesis using finite elements. Very few experimental tests have been carried out on cross vaults due to its high cost and complexity. That's the reason why we started a series of 4 tests on full-scale timbrel vaults, similar to those shown in the previous slide. During the test, we imposed vertical settlement in one of its supports, the one shown with an arrow. The main objectives of SAHC was to analyze the behavior of timbrel vaults subjected to cross settlements, study the retrofitting techniques and their efficiency, and propose also monitoring patterns. So we designed a series of tests on 2 full-scale timbrel cross vaults made on the laboratory. The cross vault had a plan of 4 by 4 meters and a height of 2 meters. To simulate the presence of contiguous vaults and therefore constrain horizontal displacement, the 4 sides were braced with a steel framework on its base. The vaults and the tests were designed using preliminary finite element models. In the foundation steel formwork, 3 of the supports were free to move horizontally, and 1 was fixed. Then, in support number 1 was the one where we imposed the vertical settlement. In this video, we can see the construction of one of the cross vaults. First, the 4 arches were built, supported by a metal formwork. This is the only place where a formwork is going to be used. This formwork was removed after 48 hours. The arches were made with 4 layers of bricks, first joined with plaster, second to fourth with lime mortar. Once the arches are built, the shell or web was added in the form of 2 layers of bricks. The first consisted of bricks and plaster with a very fast hardening. The second layer was laid perpendicular to the first using bricks and lime mortar. We can see in the video one of the main beauties of this type of structure. Once the arches are built, it's self-stable during the whole construction process, without the need of a formwork. That made this structure very efficient, very fast to build, and well, very structurally efficient. Also need more than a builder, it needs an artist. The position and type of sensors was defined according to the model, finite element model results. LVDTs were placed close to the support where displacement is applied. Some critical cracks were expected there. LVDTs and fiber optic sensor were also applied in the shell. Some also critical cracks were expected. Strain gauges were placed in the supports in order to measure the reaction. And finally, LVDTs in one of the supports to measure vertical displacement. Also, some tests were carried out in order to characterize all the materials: concrete, lime, mortar, bricks, etc. And then the whole setup were also tested with different positions of bricks. 2 cross balls were tested. We can see here in the video the test of the second one, in which we try to simulate the behavior of expansive soil with shrinking and heave of the soil. So the support was going upwards and downwards. The displacement was applied with 2 synchronized jacks. Both cross balls were repaired after being tested. This means that the balls suffered previous damage. We can see in the video the procedure to repair the 2 cross balls. First, the cracks were repaired with pre-dosed lime root. Then we applied the mortar. We can see that we applied the mortar in the diagonal of the cross ball and also in the arches, and then in the keystones. Then, once the mortar was applied, then the TRM was placed, and finally a second layer of mortar. And now we are going to see the main results of the test. We can see here first the settlement that were applied to ball 1. You see it's a monotonic settlement going always downwards, and then the settlements applied to ball 2 that were downwards and upwards. Trying to reproduce the same behavior of the heaving, the heaving and shrinking of expansive soil. We see here the results in one of the balls, the one subjected to downward displacement. We see here the reactions in every of the supports. Displacement was applied gradually, as we saw before, and then figure shows the evolution of the support reactions according to the vertical displacement imposed. We see here that reactions in support number 1 and support number 3, support number 1 is the one going down, they decrease as the test advances, and while reactions in S4 and S2, the one in the diagonal, they increase. After 10 millimeters of settlement, the first cracks appear, and then the reaction in support number 1 and support also number 4 remain fairly constant. We can see here also the results in ball number 1. This is the envelope of maximum and minimum reactions during the test. We see again that once 10 millimeters of settlement is reached, then the reaction in support number 1 also remain fairly constant or even decreases. We see here the main pattern of cracks that appear during the test. The cracks were the ones expected according to the finite element models. One of the archers suffered serious damage in support number 2. After 35 millimeters of settlement, base support in support number 3 failed. The tests were stopped at 39 millimeters of settlement. After TRM strengthening, we reproduced the same test, and we see here the reaction of the support. The picture shows the results of the test carried out after this strengthening, and we can see here that the displacement reached up to 20 millimeters, a little bit more than 20 millimeters before the plastification, before the reaction of the support remained constant. Not only in vault number 1, but also in vault number 2. We see here that the displacement reached almost double that were reached before the strengthening with TRM. And again, we see here the crack patterns that we observed during the test with TRM. We see how the imposed displacement in these cracks appear much farther than appeared at the beginning in the first test, and also they reach a higher displacement before breaking down. And the same in vault number 2. I have to say that even though they were subjected to much more displacement and they resisted much more displacement, its behavior was also much more fragile than the one observed before the balls were strengthened. The main conclusions drawn from this test were, well, we tested two full-scale timbrel poles for tests before and after strengthening. The maximal displacement reached was 39 millimeters. We had to stop the test due to serious cracking in the keystone and arches. The tests were stopped for security and also to facilitate future repair. Support number 1 allowed 25% of its original reaction during the first test. Also, reaction in support number 1 were constant after 10 millimeters of settlement. Crack in the keystone, the arches S4 and S2 were forecast by finite element models, and the width of the cracks observed was 2.5 millimeters. The RM strengthening doubled the bolt's elastic phase and ultimate displacement. And then we have ongoing research trying to take profit of all these tests with more advanced finite element models, a parametric study, and also in order to propose new monitoring patterns. Well, I hope you enjoyed the presentation. Thank you very much for your attention.